Okay, let's start today's class. 4 topics today. Solve a general linear system from section 1.2, then vectors from section 1.3. Before I present the topics, let me add some remarks about epsilon form and reduced epsilon form. Remark number one, epsilon form of a matrix is not unique. Not unique, that means that epsilon form, there was many epsilon forms. The step-like pattern of an epsilon form is unique, but the entries in the epsilon form depend on the operations that you use. The entries may be different for epsilon form. Epsilon form. This is a remark number one. Remark number two. How about reduce epsilon form? But reduce epsilon form is unique. Yes, please mute because I can hear, some noise. Okay, yeah, please mute. Yeah. Reduce epsilon form of a matrix is unique. That means that the step-like pattern, okay, all the step-like patterns are the same, and the entries in reduced epsilon form are also the same. Doesn't depend on the operations that you use for reduced epsilon form. Number 3, C. C. Pivot entries, the pivot numbers, depend on the operations, the row operations that you use. Okay. Pivot entries, the value, the numbers depend on the operations that you use. However, pivot position, okay, pivot positions and pivot columns don't depend on the operations that you use. Okay, these are the remarks about epsilon form and reduced epsilon form. Okay, now let me start today's topics. Topic 1, solve a general linear system by using epsilon form and reduce epsilon form. Okay, take a look at examples. Take a look. Okay, this example. Example 1. Solve this linear system. The second equation is The third equation in this linear system, the number of unknowns is 5 and only 3 equations. So this is a rectangular linear system. Now, I work on augmented matrix rather than work on equations. Augmented matrix is the first row corresponds to the first equation. The first equation coefficients are 0, 3, -6, 6, 5, 4, then -5. Second equation coefficients are 3, -5, 8, 9. Third equation -15. And separate the last column from the other columns by a vertical line. The last column is right-hand side. Now, to solve this linear system, I first simplify augmented matrix into epsilon form. Okay. Forward elimination. Reduce the matrix into an epsilon form. Because the 1-1 entry now is 0, I cannot use 0 to eliminate other entries. So I switch the first 2 rows. Row 1, row 2, switch. Then I get row 1 and row 3. I switch row 1 and row 3. Then I get 3, -9, 12, 6, 15, 3, 7, 8, -5, 8, 9, 0, 3, 6, 6, 4, -5. Now, I use this number as my pivot entry, pivot number, pivot entry to do elimination. -1 times row 1 add to row 2. -1 times row 1 add plus row 2. Plus row 2. Put the result in row 2. 3. The first row is not changed. 6, 15. Second row is changed. 2, -6. Third row, not change. 4, -5. Okay. The second step, I use this number to eliminate the number 3. This number is my pivot entry. Or you can, because I can see that, all the entries on the second row has 2. So it's better scale row 2 before elimination. But let me use 2 as my pivot entry. Then negative 3/2 times row 2. To eliminate number 3, plus row 3, put the result in row 3. Then this number is gone. 3, -5, 12, 9, 6, 15, 0, 2, -4, 4, 2, -6. Then row 3 is forward elimination is done. Forward elimination now is done. This final matrix is in epsilon form. But this linear system still not simple enough, because I still can introduce zeros to the matrix. Now, next, I perform backward elimination to get reduced epsilon form. Now, backward elimination. To get reduce epsilon form. I start with the rightmost pivot entry. Okay, 1. I use this one to eliminate the numbers above. So -2 times row 3 plus row 2. Put the result in row 2. Then this number 2 is gone. I get 3, 9, 12, -9, 6, 15, 0, 2, -4, 4, then 0, -14. Row 3 not change. Continue. This number is my pivot entry. Now I use this number to eliminate the number 6. -6 times row 3 plus row 1. Put the result in row 1. Then row 1 is 0, -9, row 2. 14, 0, 0, 0, 0, 1, 4. I can see that we still can introduce zeros to the matrix. I can use 2 to eliminate -9. So 2 is a pivot entry. Positive 9/2 times row 2 plus row 1, then -9 becomes 0. Put the result in row 1. 3, 0, -6, 9, 0, -72, 0, 2, -4, 4, 0, -14, 0, 0, 0, 0, 1, 4. Now you cannot introduce any more zeros to the matrix. Some people may say that, how about I use, say for example, -4 to eliminate -6. But if you use -4 to eliminate -6, then this number will introduce non-zero number here. So we cannot introduce any more zeros to this matrix. This final matrix are very close to reduced epsilon form, but reduced epsilon form requires leading entries or are 1. Now, one more step, scale the rows. Scale the rows. 1/3 times row 1. Put the result in row 1. Scale row 1. Then 1/2 times row 2. Put the result in row 2. Scale row 2. Then we get reduce epsilon form. 1, 0, -2, 3, 0, -24, 0, 1, -2, 0, 7, 0, 0, 0, 0, 1, 4. This linear system, this is the augmented matrix of a linear system. This linear system is simple enough. Pivot positions are this position, pivot position. First column is a pivot column because the first column contains a pivot position. This position, a pivot position. Second column, pivot column. And this position, pivot position. The 5th column is a pivot column. The first column are the coefficients of the variable x1. Second column, coefficients of variable x2. Similarly, this is a x3, x4, x5. X1 corresponds to a pivot column. First column is a pivot column. X2 corresponds to a pivot column. Column 2, pivot column. X5 corresponds to a pivot column. The 5th column is a pivot column. Okay, so we call these 3 variables, give a name to them. we call x1, x2, x5 basic variables. Basic variables, their corresponding columns are pivot columns. How about x3 and x4? x3 and x4, their corresponding columns are free columns. What is a free column? A column that is not a pivot column is a free column. So we also give a name to x3, x4. Okay, we call x3, x4 free variables. Free variables, that means we can freely assign values to x3 and x4. Okay, now next step, write the final matrix in equations. Yeah, this final matrix, let me write it in equations. In equations, the final matrix or matrix is the following linear system. First row is an equation. The equation is x1 minus 2x3 plus 3 x4. x5 coefficient is 0. So low x5 is equal to right hand side 24. Second row is an equation. Coefficient of variable x1 is 0. So second equation has low x1. Second equation is x2 minus 2x3 plus 2x4 and also low x5 because the coefficient of x5 is 0. Then is right hand side. Third row, x3 is 4. This linear system is simple enough. Okay, now
wouldn't it be x5 equals 4? Wouldn't it be x5 equals 4?
Rather than x3, correct. Thank you. X5. Okay, now next, to get the solution of the original linear system, now solve basic variables in terms of free variables. Basic variable, yeah. Basic. Free variable, x3. Now let me solve the linear system for basic variables in terms of the free variable. The first equation, let me move free variables to the right side. Then again, x1 is negative 24 plus 2x3 minus 3x4. Second equation, let me move x3 and x4 to the right side. Let me 7 plus 2x3 minus 2x4. Now that equation, a low free variable, that equation is S1. Yeah. These are all the solutions of the original linear system. Where x3, x4 are free. What it means, free. Arbitrarily assign values to x3, x4. Okay, this is the general solution of the original linear system. A general solution means all the solutions. For example, if I said x3 is 0, x4 is 0, plug in 0 in the first equation, then I get x1 is -24. Plug in 0, 0 into the second equation, then I get x2 is -7. X5 is always 4. Then this is one solution of the original linear system. The solution is, okay, x1 is -4, x2 -7, x3 0, x4 0, x5 4. This is one solution of the linear system. Now, if I say x3, for example, is 0, x4 is 1, then plug in 0, 1 into the first equation, then I get 0 and 1, then I get x1 is -27. Plug in 0 and 1 into the second equation, 0 and 1, then x2 is -0, 1, -9. x5 is always 4. Now I have a second solution to the original linear system. X1 is -27, x2 -9, x3 0, x4 1, 4. Second solution. Recall that a linear system, about its solution, only 3 cases: either no solution, or exactly one solution, and infinite many solutions. Because I have found 2 different solutions, so that linear system must have infinitely many solutions. Why? Because we can assign many values to the free variables to get many solutions. This is how to use epsilon form and reduce epsilon form to solve a general linear system. Okay. Let me make a summary about solving a general linear system. Summary based on this example. Summary. A summary of solving a linear system. How to solve a linear system? Step 1, perform forward elimination to reduce the linear system to an epsilon form. Okay. Okay, now we have two cases. Okay, case one, if the bottom non-zero row, I'm talking about augmented matrix. The bottom non-zero row, when a row contains one non-zero entry, the row is considered non-zero. Is form 0, 0, 0. Then right hand side non-zero. Okay, let me use this little black square to mean non-zero. Okay, where this symbol, okay, means a non-zero number. If the bottom non-zero is in this form, recall that augmented matrix, each row is an equation. So the corresponding equation to this row is 0 times x1 plus 0 times x2 plus 0 times, suppose the linear system has n unknowns, xn is equal to a non-zero number. Impossible, no matter what values for x1, x2, xn. This equation is never true. This case, the linear system, the system has no solution. Any example? Yeah. Say, take a look at this epsilon form. 2, 1, 0, -1, 0, -3, 1, 0, 0, 0, 0, 4, 0, 0, 0, 0. The last column is right-hand side separate. The bottom non-zero row is the third row. The third row is in this form. So this linear system has no solution. No solution, then stop. We don't need to continue with backward elimination because we know no solution. Stop here. Okay. Second case. Second case, B. If the bottom non-zero is not in this form, otherwise, the linear system has solutions, one or infinitely many. Okay. Okay. If the linear system has solutions, continue backward elimination. Okay. Now, this is step one. Step one. Now, step two, backward elimination. 2. Suppose the linear system is consistent. That means linear system has one or more solutions. Okay. Also, there are two cases. Case one, if there is no free variables, then the linear system has exactly one solution. Okay. Then how to get that solution? Backward elimination. Backward elimination to get the solution. A linear system has no free variable. Any example? Take a look at this example. Okay. Here. How about I still use this matrix, but let me move this 4 here to the free position. Okay. Yeah. 2, 1, 0, -1, 0, -3, 1, 0, 0, 0, 4, 0, 0, 0, 0, 0. This linear system has no free variables. The 1, 1 position is a pivot position. Pivot position. And also pivot position. First column, second column, the third column, pivot columns. So first column is for x1, second column for x2. These are x3. So x1, x3, x2, x3, they correspond to pivot columns. So all these 3 variables, basic variables. This linear system has only one solution. How to get the solution? Either bad substitution or backward elimination to get the solution. Second case. Okay. Also, let me make a remark about the third row. The third row is 0 times x1 plus 0 times x2 plus 4 times x3 is equal to 0. This equation has solution. The solution is 0 times x1, 0 times x2. So this equation actually is this. Move 4 to the right side, then x3 is 0. The equation has solution. The solution is 0. There is a solution. Okay. Second case, B. If there is 1 or more free variables, okay, then the linear system has infinitely many solutions. Why? When there is a free variable, I can arbitrarily give values to the free variable. So the linear system has infinitely many solutions. An example, yeah. Take a look. I still use this matrix, but I make row 3, 0, row. 2, 1, 0, -1, 0, -3, 1, 0. Then row 3, 0, 0, 0, 0. Then 0, 0, 0, 0. Last column, right hand side. Okay, for this matrix, this position, pivot position, this position, pivot position, row 3, 0, row, low leading entry. Row 4, low leading entry. So first column, second column, pick the columns. Therefore, X1, X2, they are basic variables. But X3, the column 3 is a free column. So X3 is a free variable. We can arbitrarily assign values to X3. So therefore, this linear system has infinitely many solutions. Yeah, this is a summary about solving a general linear systems. Reduce the linear system to epsilon form. Then look at the bottom non-zero, okay, to determine whether or not the linear system has solution. Okay. Then if there is a one solution or more solution, that would elimination. Okay. This is topic 1 today. Now second topic. Let me see what is the second topic. Second topic from section 1.3. Vectors. You may have a question. What is a vector? Now, let me tell you what is a vector. Okay. Vectors. Topic 2. Section 1.3. Vectors. What is a vector? Okay. What is a vector? Let me answer this question. Okay. The answer is simple. A matrix. All right. A matrix with only one column. Only one column is called a vector. Some people call it a column vector. A column vector. But usually we just call it a vector. Okay. So a vector is a matrix with only one column. For example, let me give you some examples. Example 1 under this topic. Okay. Say 3, 1, -1. This is a 2 by 1 matrix, a matrix with only one column. It is a vector. Okay. Let me give a name to this vector. Say vector A, and I put an arrow on the top to denote this vector. This vector has 2 entries. So usually people call this vector a 2-dimensional vector. This is a 2-dimensional vector. Okay. Yeah. Okay. 2-dimensional vector. Because the vector contains 2 entries. How about this? Okay. Yeah. 2 -1.9 0. Okay. This is a 3 by 1 matrix. A matrix with only one column. It is a vector. Okay. Now this time, this is a 3-dimensional vector. Yeah. Let me give a name. Let me call it say E. Put an arrow. Okay. E. This vector is a 3-dimensional vector. Yeah. This is a 3-dimension. 3-dimension. vector. Yeah, this vector is 5-dimensional vector. Point 1, say for example, different name, say vector V, say put an arrow. 5-dimensional vector. And one more, okay, say 0, 0, 0, 0, 0. This is a 5-dimensional vector because all the entries are 0. We call it a 0 vector. Okay, now usually the rotation is 0, then put an arrow on the top. 0 vector. Yeah. Graphically, okay. Graphically, how to represent a vector? Okay. Okay. Geometrically, a vector is represented by a point. I will show you example. Or by an arrow. The arrow starting at the origin. Yeah. Say for example, let me show you one example. Okay. Say example. Say consider this vector. Okay. How to represent this vector? Draw XY plane. Draw XY plane. Okay. This vector, we usually use a point to represent it. Which point? Yeah, this point. 3 negative 1. This point. 3 here. Negative 1 here. Yeah. Yeah. This point. Yeah. This point is this vector. They are the same. Okay. We consider a vector and a point the same. Or by an arrow starting at the origin. Which arrow? Yeah, this arrow starting at the origin and ending at this point. Yeah, ending at this point. Yeah. So this vector is this point. We consider them same thing. And also is equal to the arrow on the XY plane with its tail at the origin and its head at the point. Which point? Yeah, this point. 3 negative 1. 3 negative 1. So geometrically, a vector. Okay, geometrically, a vector, say vector V is equal to a point. The point located and the point, say take a look at this example. This point, x coordinate is 3, y coordinate is 1. A vector is a point and also is an arrow starting at the origin and ending at this point, at the point. So in this book, these three things we are identical. A vector is a point is an arrow, okay? Identical. This is topic 2 about a vector. Now, the next topic, let me see, the next topic. Oh, vector operations. What it means? Vectors have, we can add two vectors. We can subtract a vector from another vector. We can multiply a vector by a number. In linear algebra, a number usually is called a scalar. A scalar. Okay. All right. Now, topic 3, vector operations. Topic number 3, vector operations. All right. Number 1. Okay, first, let me suppose we have two vectors. Let vector v is this point. A vector is a point, okay? This is an n-dimensional vector because it has n entries. Second vector, v1, v2, vn. Hey. Now, operation number 1, summation. Summation. Okay. Vector u plus vector v is a new vector obtained by adding the corresponding entries. Okay, so this new vector is entry 1 plus entry 1. No. Entry 1. Entry 1, then comma. Second entry plus second entry, comma. Third entry plus third entry, and so on. The last entry plus last entry. Yeah. Addition of two vectors. B, subtraction. Vector u minus vector v. Again, is a new vector. How to get the new vector? Subtract the corresponding entries. Entry 1 minus entry 1. Entry 2 minus entry 2, and so on. Entry n minus entry n. Operation number 2, subtraction. Now, operation 3. Scalar multiplication. Scalar, a number in the context of matrices, vectors, numbers are called scalars. Okay. C is a number times vector u. this is a new vector. How to get this new vector? Multiply the scalar C to all the entries. So it is a C times entry 1, C times entry 2, C times entry 3, and so on. About vectors, we only define these 3 operations. For vectors, row, a vector times a vector, no. A vector divided by a vector, no. Row, product, row, division, okay? Only these 3 operations for vectors. Yeah, let me show you examples. Take a look. Examples. Example 1 under topic 3. Given these 2 vectors, 1, -2, v, 2, -5. Both are 2-dimensional vectors. Okay, now the question is, can you find 4u minus 3v? I can see 2 solutions. Solution 1, solution number 1. Okay. 4 times u minus 3v is equal to what is u? 1, 2, -2 minus 3v 2, -5. Okay. 4, a number, times a vector is 4 times all the entries. 4 times 1, 4, -8. Minus 3 times a vector, 3 times all the entries. 6, -15. Yeah. Then a vector minus a vector is a vector by minus the corresponding entries. 4 minus 6, -8 minus -15, +7. Yeah, this is the answer to the question. Solution 1, solution 2. Solution 2. Okay. 4u minus 3v. I can view this expression as 4u plus -3 times v. Okay. So let me. What is u? 1, -2 plus -3 times 2, -5. Then it's equal to a number times a vector, the number times all the entries. 4a plus -3 times all the entries. -6, +15. Then compute the sum of these 2 vectors. 4 plus -6, -2, -8 plus 5, 7. Yeah. Done. 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 This is our example 1. Now, second example. Example 2. Example 2. Let u be free, -1, be this vector. Now the question is, can you display the vectors u first, then 2 times u, -2 third times u. Can you draw these three vectors on the xy plane? All right, now solution. Let me draw xy plane. Okay, xy plane. X, Y plane. Okay, now let me draw vector u first. Yeah, vector u. Vector u, it is a point or an arrow. Which point? The point is 3, -1. 3 here, -1 here. So this point is vector u. Or I use an arrow starting from the origin and ending at this point. This vector. This is no, put the point here. Shift down the point. Okay, yeah. This arrow is vector u. Okay. How to get 2 times u? 2 times u is a vector. The length is twice the length of vector u. Okay, twice. Okay, so from this point to this point, the length is the length of u. Now, twice the length. So let me draw. Okay, about here. This green arrow is 2u. Because 2 is a positive number. So multiply a positive number to a vector doesn't change the direction. So the red arrow, the green arrow, they point in the same direction. Okay, now how about this vector? Yeah, this vector. 2/3 times u. Okay, first negative. That means that change direction. Okay, so this vector, the direction is opposite to the direction of u. The length is 2/3 of the length of vector u. Okay, so from this point to this point is the length of vector u. So 2/3 of the length about here. Opposite direction about here. Yeah. So this arrow is negative 2/3 times u. 2/3 times. This is topic 3. Now, the last topic today. Let me see the last topic. What is the last? Parallelogram rule for vector addition. Okay, topic 4. Topic number 4. Okay. Algebra. Basically, we add 2 vectors by adding the corresponding entries. All right. Graphically, geometrically, we add 2 vectors by drawing a parallelogram. 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 2 vectors by drawing a parallelogram Okay. The results are equal. The results are the same. Let me show you one example. Okay. Say example one. Let vector u is 0, 1. V is 1, 0. Now the question is, can you find vector u plus vector v? Okay. Two solutions. Solution one, I add the two vectors by adding corresponding entries. Solution one. Okay, this is a algebraic solution. Okay. Vector u plus vector v is 0, 1 plus 1, 0. Then 0 plus 1, 1, 1 plus 0, 1. This vector. Second solution, geometric solution. Solution two. Geometric solution. All right, now U and V are two-dimensional. So let me draw XY plane. X, Y, okay, 0. Now let me plot vector U. Vector U. The point is 0, 1. X is 0, Y is 1 about here. So the arrow, okay, yeah, this red arrow is vector U. Vector U. Vector V, 1, 0. The point, the corresponding point is a 1, 0. 1, 0 is about here. 1, 0. Yeah. This is a vector V. Okay. Now, I use parallelogram spanned by these two arrows. Okay, I draw a parallelogram spanned by these two arrows. Okay, draw a line parallel to vector V, and draw a line parallel to vector U, and through the head of vector V. Vector V. Then the diagonal line of this parallelogram is the sum of these two vectors. Yeah, the diagonal. Yeah. The head is at the point. Which point? The point is 1, 1. Yeah. This point, 1, 1. Yeah. 1, 1 is the sum of vector U and vector V. Yeah. So the sum is the diagonal of the parallelogram spanned by vector U and vector V. This is one example. Now, second example. Okay. Example 2. Example 2. Let U be 0, 1 and V be 1, 0. Now find 3 times U minus 2 times V geometrically. Okay, now solution. Let me draw XY plane. X, y plane. Let me plot vector u and vector v. Vector u, the point is 0, 1, 0, 1 here, about here, 1 about here. Okay, yeah, this vector is vector u. Vector v, 1, 0, 1, 0 about here. This is a vector v. Vector v. Okay, now is difference is, let me rewrite it as a -2 times v. Okay, now let me plot 3 times u. 3 times u is the length is triple the length of u. Okay, 3 times u is about here. 1, 2, 3. Yeah, here. This is a 3 times u. -2 times v, negative, so the direction is opposite. -2 times v, the length is twice the length of v, so an opposite direction. So here, 1, 2 about here, 2. Yeah, this vector is -2 times v. Now make a sum of these two vectors. Summation. Draw parallelogram. Through this point, the head of -2v. Draw a line parallel to 3u. A line parallel to 3u. And through the head of 3 times u, draw a line parallel to -2v. Then, starting from the origin, draw a line and to this point. Okay, yeah, this is the diagonal line of the parallelogram. Yeah. So this green arrow is the sum of this vector and this vector. This point is -2 and 3. So the sum, so the sum of this vector is equal to -2 and 3. A vector, a point, and an arrow, we view them same thing in linear algebra. This is all for today's class. Any questions?